All right, so today we're going to be doing day 11, the challenge in Advent of Code. So for the first part, we have an input, which is the input file, and each number represents a different stone. And there are some kind of magical stones because every time we blink, they change based on a set of specific rules. And there's 3 rules. If the stone is a 0, it becomes a 1. If the stone has an even number of digits, so if it is a 10, then it splits into another stone which is a 1 and another stone which is a 0. So it splits into 2 stones down the middle. If it's 4 digits, then the left stone will have 2 digits, the right stone will have 2 digits. And then of course if it's 1000 and we split it, then we will just get 10 on the left side and we won't get 0, 0 on the right side, we will just get 0. So there's no trailing zeros. And if none of these rules apply, so then the last rule will apply, which is just to take the stone and multiply it by 2024. So we will take this, for example, because it's an odd amount of digits, and multiply by 2024. So if we look at the example, 999 becomes whatever this is. And if we look at the initial arrangement of this example, we get 125, which has 3 digits, so we multiply it by 2024, it becomes this. The 17 has an even amount of digits, so it becomes 1 and 7. And then this now has even amount of digits, 253 and 000, so 253 comes here, the 0 comes here. And we keep going, we keep going, we keep going, we keep going. And after 6 blinks, this is what we get. And after 25 times, this is how many blinks we get. How many stones we get after blinking 25 times. And they want us to calculate the exact same thing, but with this input instead. So I have put the input in an input.txt file. We can include it and import it by opening it and then just reading the single line that exists. And then I will iterate for each number through the line. And we do that by splitting it with spaces. By default, it splits it by space. And I will append to the stones the number that we found that we convert to integer. Then we define a variable, blinks, and we want to blink 25 times. And we will iterate through this for loop 25 times. So 25 times we will do something. What we will do is that we will find some new stones, which we will set to the regular stones, because we don't have to keep the old ones actually. Every time that we iterate through a generation, we just want to know how many there are now and which ones they are. And then through the next generation next. So we can just forget what happened in the past. We don't really care. So there are 3 cases. So if the stone is 0, then just make it into 1. If the stone has even amount of digits, then we want to split it. So we will find the halfway point. So we will take the length and then divide it by 2, and then that's the index. And then the left half will be from the beginning to the half point, and then the right half will be the same thing, but from that half to the end. That's why there's a semicolon here. So nothing means from the beginning to the half, and then from half to the end. Now the new stones, we will append to the new stones, both of them. And in the last case, if none of these happened, then we just take the stone and multiply it by 2024. And the reason that you see me appending and extending is because we don't actually care about the order in which the stones are in. We just care about how many stones there will be. Since the children stones don't really look at each other to see, okay, should we do something else based on what's next to me? They don't do that. So we don't need to check that actually. We don't have to keep them in the same order. So we get the stones. And then eventually, once it iterates through all the blinks, we will print the length of the stones. So if we run this, also I've put this just to see how fast it goes. So it went to 24, and then the 25th, the first one is a 0, yeah. And then 24th is the 25th time that it iterates, and this is the answer, 193,000 something something. And that is the correct answer. Now for part 2. It is the exact same problem, but they are asking us to do it 75 times. So what we can do is to just change this to 75, but we will see that there's a tiny problem. And if we run it, we can see how many iterations it's going through. So it's at the 26th blink, 27th blink, and so on and so forth. So this is a really simple implementation. We just check, okay, whatever case that we need, and then we take the new stones and then we repeat again. But the issue is that this is exponential time complexity. So the more blinks that we have, the more complicated it will get. So it's gotten at 31 and it keeps slowing down, it keeps slowing down. So it might never get to 75. So what I've done instead is that I've redone the program. We still open the file in the exact same way, and we've changed it a little bit. We've implemented two things. One thing is that I've made this into a function, and I've made it into a recursive function, so it calls itself. And the second thing is that we've implemented cache. And what caching does is, if we have a stone that we will give to this function, which is process the stone, so we will give it a value, and we will give it, what do we give it? The remaining blinks. Let's call it B. So if we give it, let's say the value is 0 and remaining blinks is 1, and then somehow this function spits out a 1, then we know that every time that we give this function a 0 or a 1, we will always get a 1. So we just cache that this thing happens. So next time that we call it, we will not need to go through the entire function again. We will just check the cache and see, oh, you know what? We actually have the answer for these inputs. And since we saw in the examples that the numbers always mostly converge to really small numbers because we keep splitting them. So we can see here, there's a 2, there's another 2, there's another 2 here, another 2 here. So every time that we find the same number again, it's cached and it processes a lot faster because we don't have to do all the computation again. And sure, there will be some big numbers, but even those ones, if we keep linking, they will turn into small numbers eventually. So we've done this, and then for each different case, so if the stone is 0, if it has even digits, or otherwise multiplied by 2024, for each different case, we recursively call the process stone function, which just gives it the new value and how many blinks it has. So it will go all the way down until it has 0 blinks, and this is the base case, of course, and it will return 1, that there is that one stone all the way down when we've recursively blinked how many times we asked it to. So it will store in the cache every answer to every process stone with each value and each remaining blinks that we give it, and this will be a lot faster. But since this is recursive, I can't just print here the remaining amount of blinks because it will print it in a really weird order, so we can't really see what's going on. But if we put a 25 here and we run this again, we get the exact same answer. So now if we put a 75, the other one took a long time to just get to 30. Let's see how fast this one is with 75. So it takes maybe 1 or 2 seconds. We can put it to 100 and it doesn't get too much more complex. So yeah, it's pretty quick. I think I can even put it to 200. Eventually this is going to run out of memory, of course, as well, of course. But yeah, it works in a couple seconds with even 200. This one would really take forever to go through 200 iterations. So if we go again to 75, let's see what the answer was. It was 229 and then it ends in a 225. So 229 and ends in a 225. That's the correct answer. And now, if we look at the time complexity for part 1, it's a lot worse than part 2 actually, because of the way we implemented it. The way we implemented it is just really simplistic, a for loop, and then check all the cases. So it's not meant to be efficient, it's just meant to show that we can make it really simple. But the time complexity is n times 2 to the power of b, b being the total number of blinks that we have. So the more blinks we have, the worse it will get, and it's exponential. And the space complexity is similar as well, because we store all of the new stones that we've made. And that was the time complexity for part 1. And for part 2, since we use caching and we recursively call it, the time complexity instead is n times b times d. So for each single stone that we process, we average out on the time complexity of B times D, which is how many digits the stone has in the input, and then B, how many blinks we have. And then since there are n amount of stones, we multiply it by that. So it's not exponential, it's still a bunch of different variables multiplied by each other, not added. But this is the most optimal way that we can solve this problem. And the space complexity in this case is also better, is just n times b instead of n times 2 to the power of b, which is great. So that was problem 1 and problem 2, part 1 and part 2. And if you guys want to join the leaderboard, I will leave the, let's see, code in the description. And thank you for watching. Happy holidays and see you tomorrow.